FOSDEM ex-org boards and also vice president of software for the One Laptop per Child project. He will, of course, speak about one laptop per child. Jim?
Thank you. This is a picture of a school in rural, middle of nowhere Cambodia. It takes about 6 hours to drive there. Nicholas Negroponte built a couple schools a few years ago and discovered that the cost of the laptops were really expensive. And the cost of the fuel for generators for the laptops were really expensive. It was quite eye-opening. There's one thing I'll start with. I want to try to reset people's view of the world here. The first problem was when the kids were given laptops was persuading the parents to let them use the laptops when they were taken home, because laptops are worth more than the houses that they were going home to. Once they got past that point, the next realization of a day or two later was, for most of these kids, this was the first time there was any artificial light in their house. That's the bulk of the world. Most kids go home at night to houses with no electricity and no light. Okay, so this is sort of what I'm going to cover in this talk. In some sense, this being a geek audience, I'm going to try to adjust or explain to you why we designed the machine the way we did. We've had the luxury, which Linux people typically have, and free software people have not had, of actually being able to design our own hardware from close to scratch. This has allowed us a set of freedoms in design that you typically don't have, and is allowed us to go in directions that you normally can't do in the Microsoft ecology. At least not unless you're Microsoft. There's realities about hardware design that a lot of people don't fully appreciate. It is very different than software. There are realities of what ingredients you can actually get to make your sausage. And you can only make as much sausage as you can actually get the ingredients for. It isn't like software where you can always run off a few million more copies. It just doesn't work that way. Some parts of the recipe you can substitute. Those are called second sources. But other parts you can't. They're single source suppliers, and if they stop being able to make your component, you're in real trouble. If you make a lot of sausage, you can actually get some custom ingredients made, and depending upon how long in advance you start, depends upon how unique and new the ingredient can be. So full custom VLSI is like a 3-year lead time. You can build an ASIC in as little as 3 or 4 months if you know what you're doing. You can actually build a couple of application-specific ICs in the machines that we have here. This is the so-called B-Test 2 machine. It's the second beta test build we've done. So, in any case, what we're out to do is to educate kids or help them educate themselves. That's what we're about. We're not about free software per se. However, you will see how the two go hand in hand later in this talk. There's something of order 1 to 1.5 billion children in the developing world. This is a lot of kids. So if you do the math, how many machines per year should we be doing if we can build a machine that lasts 5 years? How many laptops were built last year? Does anybody know in this audience? I think it's like 65 million, 70 million, something like that. You can see that if we do this for real, we should end up building a lot more laptops than everybody else put together. This is the reality of what a school in the capital city of Nigeria looks like. Okay? This school is fortunate. It has electricity in one room. There's no lights, no nothing in the regular classroom. And that's the capital city. You go outside of the capital city of Nigeria, it doesn't get better, it gets worse. Another picture of kids from that school, I believe. Another thing I want you to think about is again, I had breakfast with someone this morning who had never focused on the fact that most kids only get, say, 5 or 6 years of elementary education. So the people we are trying to serve, the kids we're trying to serve, are the young kids, not the middle schoolers, not the high schoolers, to which we have been primarily catering. We're trying to fundamentally help kids who are learning to read and getting their very basic education. And in some parts of the world, however, what we consider, what you consider a basic education is quite interesting. I was talking to a guy named Greg Mortensen, who's been building schools in very northern Pakistan, and by the time those kids leave 5th grade, they have learned 5 languages. Quite impressive. But you have to. In any case, if we just continue the way we're going, that's a risk by itself. Doing nothing is a risk. Computers and education in the developing world is quite old. That's an Apple II. Seymour there, who unfortunately was badly injured a few months ago. This is, I think, from whenever Apple IIs were current, so that would be late 1960s or something like that. So this is not a flash in the pan. The difference is we're trying to do this at scale because we believe that there are network effects that take place when every child has a machine. We're called one laptop per child for a very good reason. We don't believe that sharing machines or computer labs are an effective way for kids to use them. Do we share our pencils? Very hard to use it as a basic, as your book. If you're trying to share, it's hard for 2 people to read the same book at the same time. So we're really mean when we say one laptop per child. It's the basic premise of the project. Okay, so there's lots of interest from all over the world. We're likely to launch in the countries that are green here, though Thailand is iffy, courtesy of the change of government. That always makes things much more entertaining. Governments are not necessarily stable. Our premise is that kids all over the world, and this is true so long as they get a decent nutrition, are just as bright all over the world as they are here. So we think that if we can get machines into the hands of every kid, that this is a really fundamental tool. This presents a huge set of challenges, though, of course, you might imagine. Another point of view is we don't believe that kids are just passive consumers of, quote, content from the content providers of the world. We believe that kids are creative. Those of you who have children, almost certainly your children keep journals, at least in their early years. As you may know, reading and writing are intimately related, and so writing a journal is something that's fundamental. I've watched my own daughter now in 5th or 6th grade able to actually write English reasonably well, which is quite remarkable. This is a program called Can-Can that's under development. This particular version isn't out yet, but the intent is for kids to be able to compose their own music. The other thing is we want kids to be able to experiment. Okay? This funny gizmo on the left, we did this for a demo of the so-called APES boards at a conference last May or thereabouts. That's a photocell on the end of a wooden spoon. The photocell costs less than $1. This allows you to conduct music because you can detect what the light is and figure out what the rhythm that you want to get just by detecting what the light is. So we want it to be very easy to plug things in. So one of the unique things about this machine is that the audio port can also be used just for DC in. You can use it as an A to D converter rather than just for audio. The network is really fundamental. We want the kids to be able to share. We want kids to be able to work together. If you watch your own children with their friends, you'll often see 2 kids in front of a machine busily teaching each other about the particular thing they're playing with. Similarly, we want the teachers to be able to work with the children. So the network is really fundamental. However, this again brings a whole set of huge challenges. There is no infrastructure in many parts or most parts of the world. How do we get the network out to the middle of nowhere? So there's, so we believe it's just as important that the kids communicate with each other as with the internet. Now we want them to get at the internet in a serious way. So the intent is in fact to get internet connectivity to all the schools. Depending upon where you are, there's either good or terrible connectivity. Thailand, for example, has 30,000 schools. They claim to have connected all 30,000 of them. On the other hand, if you go to Nigeria, you get a very different answer. Our point of view is that you can actually build networks on your own very cheaply if you know how. And the other observation is for a lot of things like cell phones, the bandwidth that isn't being used, it goes onto the floor. So there's interesting games you can play by governments twisting arms of cell phone carriers to allow the bandwidth that's not being used for revenue-paying phone calls to go toward internet connectivity. This is something in the middle of nowhere, and I think it was Pakistan, done some years ago, setting up a network. This is going across the disputed border from Pakistan to Kashmir, if I remember correctly. These kind of radios are now very cheap. You can build them out of 802.11. This is a picture taken of somebody hacking away in downtown Athens, it turns out, making their own network out of cheap components. So what we're intending to do out of all of this is actually ship what's called mesh networking. The individual computers are able to forward packets on behalf of nearby computers. You also notice that we actually have antennas that stick up. That makes a significant difference in the sensitivity of the radios. James Cameron has been doing experiments in the outback of Australia, which is about as good as it ever gets. So it's at least one extreme of what you can do with 802.11. Even without directional antennas, when he's had line of sight, he's gotten up to I think it's nearly 2 kilometers, which I'm really amazed by. I don't think that would be, the more realistic thing, of course, is sort of 400 meters. And then, of course, when you start thinking about meshes that get interconnected by various point-to-point sorts of links. And then you have to backhaul however you can back to the internet. So that's the kind of architecture that we're working on. I'll talk a little bit more about how that's driven the hardware design here. I'm going to go into what our design trade-offs have been, since this is not the typical laptop. Obviously, we care about it being safe, and you really don't want to have a 3-kilogram laptop on a 6-year-old. Okay, it needs to be pretty light. We also have a feature that it can be smaller than usual, because guess what? Kids are a lot smaller than we are. Kids like things that look like toys. It has to be low power. Some people think, oh, we should ship all the laptops and/or desktops we don't use anymore here to the developing world. Well, as I demonstrated before, the numbers don't work just in terms of quantity. And then you think about the power plants required to power these things. Conventional laptops are often consuming 25 watts. You ship 1 million laptops, that's 25 megawatts. Is this wonderful? You really need to worry about things like power at scale. So obviously we have to make these things cheap if we're going to, or inexpensive, if we're going to be able to build them in any sort of quantity. So our big challenges are infrastructure. How do we get, what kind of power? How do we get connectivity? Obviously, as Thailand has unfortunately been demonstrated, political instability is also a major challenge. We have to worry about physical environment. Kids don't get on school buses in the developing world. They walk home. We would like the machine to survive getting rained on, at least when closed. So we worry about that that sort of thing. You will notice it has a rubber keyboard. It isn't that it isn't that the keyboard is less expensive that way, though that may be true. It's that we have to worry a lot about water and dust. And so a conventional keyboard will not survive. So in any case, there are other indirect costs we worry about, which is if our software is big and bloated, we have a problem. I think Vista has shown how big and bloated things can get. We need to fight this tendency hard in Linux. I believe people are beginning to take this more seriously. So now let's go down to where the costs go in most laptops. And if you try to make a really inexpensive laptop, it turns out that sales and marketing would be your biggest single expense. So basically, we have Nicholas Negroponte traveling the world as our president of marketing. He's quite an amazing force of nature, shall we say. And then there's a lot of expense that goes into supporting big loaded software. And another major cost is the display. The flat panel display on your machines are expensive, and as you'll see, they also won't even work where we need to be able to have a display work. Typical laptop today is often consuming 20 or more watts. Think 1 or 2 watts, okay? But, so, something a little over a year ago, we got together and to really go through our first major design review and understood that building a machine which looked like it was going to take a steady state power of something of order 2 to 3 watts was not good enough. And the reason why is the reality of the first point. A small kid cannot generate much power. We want to have a situation where the child can rely on power being available by being able to generate it themselves with some sort of a hand generator. It turns out that a crank in the machine is a bad idea, so that there are several generators being made as external devices. We really want the kids to spend most of their time actually able to read and write and the like. So our goal has really been more like 10 to 1. I mean, if the child has to generate power, we want them to not be spending most of their time generating power for the machine, that sort of thing. And then there's another observation we figured out, which was that the mesh network demands the wireless be on, preferably all the time. That's an interesting problem. If the CPU's on all the time, and the CPU's taking a couple of watts, the numbers don't add up very well. So, and in particular, if the child's not confident they'll be power when they need it, the first thing they'll do, being the inventive little creatures that they are, will be to try to disable the wireless so they'll have power when they need it. So we finally realized that most of the time when you look at your laptop, not much is going on. The screen's being refreshed and we're forwarding packets, and that's it. Most of the time your CPU is doing nothing. Why is it on? Tell me again, why is your processor on? Why are the processors in the audience on now? How many of you are actually using your machines this instant? I don't see anybody's hands go up. Well, yes, the wireless isn't working, which means I actually have an audience. So necessity was the mother of invention. So from our point of view, we want to keep the processor off as much as possible when you're in a situation where there isn't much power available. And leave the wireless able to work and possibly the display on so the kid can be reading something. So how do we solve this problem? Well, there are two solutions to this, one piece of it is what's called a decon chip that we designed, which allows us to leave the display on, the LCD on, and turn off the processor board. So we can have the screen on and turn off that CPU, which even on a low power CPU would still be consuming a few watts. That costs us, I don't know, something probably $5 or $7, something like that, by the time all is said and done. There's a small RAM chip that does the display. We also made a deliberate decision to use a wireless chip that nobody had heard of, made by Marvell. It actually has an ARM9 processor in it and about a quarter megabyte of RAM. And so it's able to forward packets even if the CPU is off. Okay? That's why we selected the Marvell chip. There is no other chip like it on the market right now. So, at the end of the day, depending upon what you're doing, we think we'll be down in the sort of 1.5 to 1.5 watts area, depending upon whether you're using the screen or wireless, that sort of thing. So we think with 22 watt-hour batteries, we should have pretty long life. This is a typical number, obviously. Obviously, a piece of this is how quickly can we wake up the machine. If we want the machine to appear to be alive, and yet we were suspending it right and left, we're going to have to wake up the processor quickly. And it turns out the geode is not ideal. It takes about 25 milliseconds to do the wake up, but it takes about a frame time to get the display back from the decon chip. So I think it'll be about 50, 70 milliseconds sort of things. So this is just at the edge of human perceptibility. I did some measurements on an iPad handheld, and it showed that from the time that it came out of reset to when Linux was able to schedule processes took about 10 milliseconds on a 200 megahertz firmware. When I've asked the kernel community how long does it take to come out of suspend, it was a very fun trick question for a good part of last year. The typical answer was in the 1 to 2 second range. The reality is it should be measurable in milliseconds. Okay, so there are other things we'll do, like drive the panel slowly whenever possible. This isn't particularly novel to us, other people are doing this sort of thing. Obviously change the rate at which we update the screen depending upon you're doing it. The screen itself is very novel, as you'll see. As I was talking about before, we're using this Marvell chip, slightly more detail about it. Marvell's implementing a standard in development called 802.11s. So it's able to do forward packets without the processing on at all. We're just bringing this up right now in a more serious way. That's what was going on last week. We showed that it was technically possible to do by about 8 or 10 months ago. Now we're making it happen for real. We obviously care about power management in a really serious way. Most notebooks are often taking 10 seconds to wake up. I want to wake up in under 100 milliseconds. I think that's really doable. So the other thing we obviously had to worry about was cost. So this is really made much more like a consumer electronics. It's injection molded plastic. You need volume to afford to make the plastic injection molds. They're hideously expensive. They're by far the cheapest way to make a thing if you're building it in high volume. But you can't afford to do it unless you are making things in high volume. So you have a chicken and egg problem. You must have large volume in order to get prices down. We're also getting rid of most of the distribution costs. Basically, what's happening is the countries will be ordering directly from Ponta, which is the ODM involved. For those of you who don't know what ODM is, most laptops in the world are actually built by a set of companies who you've never heard of. Quanta Computer is the largest of them. 1 out of every 3 laptops in this room of almost any manufacturer that you care to name is made by Quanta, so we have the 1,000-pound gorilla working with us. It's really quite fun to see how that operation works. Oops, I hit the wrong button by accident. Okay, so we think the power will be way down. The 12 watt worst case is if you have all 3 USB ports sucking as much power as possible. The more typical things going to be down in the low ranges for most things we're doing. It's not a very fast processor. sort of what we all had for 5 or 7 years ago. It's a GX2. We have 128 meg of RAM. Thankfully, OpenOffice is not something we want to inflict on an 8-year-old anyway. So that's not a problem. So in fact, most software just works. There's megabyte of serial flash for the firmware we'll get to in a moment. Some USB ports, there's an SD card slot, the wireless audio. There's also a camera in the machine, and half a gigabyte rather, NAND flash using Dave Woodhouse's JFSS2 file system. That does data compression, so for typical programs and data, it feels more like something about twice that size. We also have a new touchpad. Whether we're actually going to ship this or not, I don't know yet, because we're still slightly over budget. We may pull it out, I don't know. But in fact, the one here, which I have, can either be used as a conventional touchpad, or the larger area can be used as a stylus for learning how to write, strangely. There's a VGA camera, so the kids will be able to take pictures. This is very, so the idea is still actually right. Okay, so I want to speak a little bit about power systems design. This machine will take more or less anything nominally between 12 volts and 24 volts. You can plug it directly into a car battery. It isn't like where you need one of these, bricks that are expensive that produces exactly 18.5 volts, because guess what? Lithium ion really likes exactly the right voltage to charge. And we know what happens with lithium ion if something goes wrong these days, as Ellen Cox demonstrated. So we are not using lithium ion. Our original intent is going to use nickel metal hydride. We're also going to be using another chemistry that's just becoming available, which is not lithium ion, but another lithium battery chemistry that is similarly safe and ecologically friendly. Lithium ion also ought to be recirculated. We're trying to make, we worry a lot about what the lifetime is. A notebook manufacturer sees batteries as a profit center, and so they're perfectly happy to have you buy a new battery every year because you've recharged it 300 or 500 times, aren't they? That's not adequate for us. So we worry a lot about making sure that it's possible to charge the battery many, many times. There's a gang charger that we just got the first samples of back, which has a car battery in it. You can charge 10 batteries at once, that sort of thing. And there's also the solar cell panels that will feed it. But also the ultimate fallback for the kids is generators. There's a crank being built. It's also a pull cord device that looks very promising if we can make it electrically robust. That some Media Lab, former Media Lab folks have started a company called Potentico to build. That's much more efficient than a crank. The crank only uses the little muscles in your arm, and a pull cord, you get to use your shoulders or you can use your leg, that sort of thing. Much better idea. The display itself, it is a new and novel display. It costs maybe 40% of what a panel of this size would normally cost. Most of the cost of an LCD is not the LCD. Most of the cost of what you have in front of you is, in fact, in the 3 color filters, in a fluorescent light bulb, which is high voltage and therefore requires an inverter, and that costs money, and how to drive the electronics. What's more, a conventional display does not work in bright sunlight. And many or most kids in the developing world get taught some or all of the time out of doors. So we have to have a display that can actually be used in bright sunlight. So conventional flat panels, even if we could afford them, which we can't, don't work. Mary Lou Jepson, who's our CTO, has invented a new form of LCD In color mode, it's backlit, and we have this funny pattern you see, red, green, blue, and so on. In front-lit grayscale mode, it's a 200 dpi display. Okay, so this thing is 1200 by 900 resolution, so we have a lot more pixels on the screen than most of the laptops in this room. We want people to be able to read books nicely, that sort of thing. In color mode, depending upon the ambient lighting, the resolution is anywhere from about 800 by 600 if there's no ambient light. Remember, in this situation, you actually still have intensity information occurring at every pixel. So the effective resolution, spatial resolution, is not a simple, there isn't a simple function where you say, oh, I just meant I have 1/3 of the pixels, therefore it works out to the following resolution. So as the ambient light goes up, the color saturation goes down, but the effective resolution of the display is going up. This is a complex situation. However, if you do test patterns in a fully dark room with backlight, the worst case is around 800 by 600 sort of resolution. In a lot of other environments, it's effectively somewhat higher. The power consumption is very low. We do not use the fluorescent light bulbs, we use LEDs. They are color-matched LEDs, but we don't care that the color fidelity is exact. And so we can take basically all of the manufacturer, all of what the LED manufacturer does. So it costs us $1 or $2 for the strip of 12 LEDs, which are also replaceable because part of the problem is in places like Libya, the lifetime of the LEDs at elevated temperature is expected to be something like 3 to 5 years. So they may need to be replaced once during the life of the machine. And that's possible to do, so we can actually replace that pesky backlight should it fail. So at worst case, this display consumes about 1 watt of power. Okay, most of your displays in the audience here are taking between like 6 and 8 watts of power. In grayscale mode, at 25 hertz refresh, this display takes about 100 milliwatts. Okay, so this is a fundamentally different flavor display than you're used to. As I said, part of the trick of making our power budgets is being able to turn off the CPU. Obviously, we have to leave the DRAM being refreshed, but not active. And so there's usually a chip between the CPU and a TFT called a Tcon. We added a megabyte of memory and ended up with what we call the Dcon. And it drives the funny pixel thing for us. It also can do some color anti-aliasing, that sort of thing. So this is part of how we get to the point where we can leave the display on and turn the CPU off. So we're going to do suspend the RAM. So let's see. So this is sort of the difference between what would normally be. So you added the Dcon and then native RAM. The other ASIC we built is a thing called Cafe. This is called sliding down the slippery slope. The Geo turns out to have a NAND flash controller, which, shall we say, sucks. So we had to do something. And once we had to build a chip to interface to NAND ourselves, we also, the countries wanted expandable flash, so we added SD and also a camera interface out of the whole thing. So that's the other chip we did. The dual mode display is actually usable in sunlight, and that, for example, is a picture of a real classroom out in the sunlight. This shows conventional IBM ThinkPad in bright sunlight and how much you get to see, and there's our display next to it. Okay, so I'll quickly run through what, we did a lot of, oops, I guess we've lost some of our pictures. My regular laptop's in the shop and I'm having real trouble. This is what a production line looks like. This is the first machine built in November. I had fun watching them build the second build of 3 or 4 weeks ago of machines. We went through a whole pile of pictures we are going to be able to see of different mechanical designs. So a lot of the mechanical improvements will be in the next so-called B-Test 3 unit. We worry a lot about safety. There's no hazardous substances in this. We're trying to make something that doesn't have sharp corners or edges in case somebody falls onto it. We're trying to make it as moisture and dust and dirt resistant as we can. That sort of thing. You will note things like, guess what? One rope and you have a shoulder harness for this guy. That's why there's 2 holes. What the ultimate environmental difference between using conventional textbooks with all the paper, which actually is not very logically friendly, versus building electronics is a very interesting question. We're having some people look into this, what the environmental differences are. Making silicon is also interesting. So I don't know what the wash is, but environmentally it's not obvious that it's any worse. Okay, I want to move on quickly to software. We care about open source from the point of view is we want the kids to be able to learn computing and the teachers to be able to do so. We want them to be able to those who are interested to really get those. We're obviously worrying about software bloat in a serious way. We're worrying a lot about system security because we're building a very large ecosystem. We hope to build 5 to 10 million machines next year, and that would make us a very big target. The other problem is theft, where we'd like to be able to detect theft in a way. Sun opened up what's called open firmware without even a press release. So we're using that rather than a conventional BIOS. We had used Linux as bootloader for a while, but open firmware ended up being a better bet. Linux is big enough that getting everything shoehorned into 1 megabit or 1 megabyte flash was an interesting challenge. We care a lot about having complete control. We're using Linux BIOS and open firmware for this. This allows us complete control over the resume path. And so we aren't running through ACPI stuff, which when we measured it was tens of milliseconds. Even if the BIOS doesn't do other stupid things. I've noticed BIOSes that seem to want to sit there for 10 seconds for arbitrary reasons, probably having to do with the worst case that some device out of some USB might ever do. We also want kids to be able to see how machines really work. There's a basic set of applications being worked on. A user environment. Remember that our user interfaces have been designed for adult, developed country office workers, not 6 or 7 or 8-year-olds who are just learning to read. Do you think that this is a good match, folks? Do you think our conventional desktops, whether they're GNOME or KDE or Vista or Macintosh, are a good match for young kids? I don't think so. What we care about is enabling collaboration between the kids and their teachers in a really serious way. And a UI that's approachable and discoverable by the kids. There's a concept of a Zoom interface where this is the local machine, and you can see your buddies, and then everybody who's on the local mesh. So we are bringing the facilities for collaboration and making collaborative applications really very far forward in the UI. So again, this is the different sort of modes, and this is a mock-up of the journal that's being built right now. So here you in the upper right-hand one, you're seeing a bunch of sets of kids working around common activities, whether they're browsing the web or PV or stuff like that. If your application is big, slow, and power hungry, I'm afraid that you're out of luck. We often have a lot of choices for any given tool. We obviously care about small and simple. So AbiWord is very nice, but it's too much for a 7-year-old. It's great for my 12-year-old, by the way. She uses AbiWord in preference to either Microsoft Office or OpenOffice. just because for a 12-year-old, that seems to heavy word, but it's just about the right thing. But for a 7-year-old, it's too much. So the heavy word folks are building a nice simple version for the younger kids, which is great. And again, there's also a collaborative aspect to heavy word these days. There's lots of ways in which we can use help. I have machines to give to people who are helping us. I even have a couple I'll probably give away while I'm here. Some people question, well, why do we use GPK and Pango? It turns out that has the best localization ability. We care about languages in a way that language coverage in a way that is really fundamentally looking at that. That's really too bad. The two things I really wanted to show most, I can't show. I have this wonderful logo for people who work on blood. It has an overweight tux, very sad, with the international symbol of, well, so, this is bloatbusters. Who are you going to call? We call it ourselves. Let's fight bloat. We want to keep tux, his svelte, slightly pudgy self. Well, it was in the files that didn't. It was in the presentation, so it lost. Macintoshes have their problems. What can I say? Macintoshes have their problems. Okay. We care a lot about end-to-end services. We think of servers as performance optimizations rather than being necessary. So for example, our chat system we're worrying about uses a Jabber-like or a protocol, but will work even when we don't have the server accessible, because we want kids who are in a village someplace away from the school to be able to still chat, right? So think about that sort of thing when you're doing things. We really can't have system management in any formal way. Courtesy of things like Avahi and Anycast and so on, a lot of the manual configuration really can go away now. So we hope to, or where we are now is we just built our second build of machines. There'll be a third build later this spring, at which point we'll do much larger education trials. And it looks like end of July is when we should end up in high volume mass production. And I want to end by saying thank you. This project, without your efforts over many years, would not be possible. So thank you all. Yes, sir.
Slightly nerdy question.
We're all nerds here.
You said the screen was 1200 by 900.
Yeah.
You said the decode chip had a meg of RAM. That doesn't quite fit.
6 bits per pixel. The pixels are packed very carefully. If you do the math, you can just fit that into a megabyte. Good question. A very nerdy question. But yes. LCDs give you, in reality, about 6 bits of grayscale. Okay? So that's the answer to how that works, barely. Yes, sir.
If you're thinking about making the web out, you need to learn OCL to the client, or will you use localization?
Well, to begin with, a lot of applications still need okay, the question is how do you do localization if you're using mostly images? It's indeed the case that icons are not completely transferable culturally. They're more so than text is. But yeah, I can imagine we're going to have to to build different icons for it. Understand, we want the kids to learn to read and write. We really do. It's just that the machine has to be usable by a child who's just in the process of learning, right? One last question. Gentleman there, the red shirt.
Well, since the first time I saw a picture of the laptop, I have this question. The antennas outwards.
Yeah.
I'm afraid they will break off easily.
Well, actually, right now they break off easily. This is not a feature. In the next build, we're making them rubber, so they'll bend, and they'll bend enough to push them around on the axis. And that, again, that's a very good question. These were not strong enough. I mean, yeah, there have been people who've been taking these machines and dropping them on the marble floors. Yes, on purpose. I mean, several hundred machines have, after they went through thermal testing and so on and so forth, ended up being tested until destroyed, so we could figure out what needed to be strengthened. Okay. Now, a few of the strengthenings are in this version. The next version, the so-called test 3 machines, will have most of the results of that work, making it a more robust machine. It takes a long time to modify injection molding molds. The lead time on those are quite long, measured in months. So you can turn new PC boards much faster, and you can do sheet metal much faster, but new plastic, it's expensive and it takes a long time. Thank you all.